graph, CFG, and data flow graph, DFG. Example 1 for control flow graph. Calculate the grade based on the score. If score is greater than 90, the grade is A. If score is greater or equal to 80, the grade is B, so on and so forth. So what is the input? The input is score and the output is grade. So the process is determining the correct grade based on the score using nested if-else control structure. Now the question is, how do we prepare the control flow graph? Okay, how do we prepare the control flow graph? So to prepare the control flow graph, we start from top down. We begin with the first if. The first if has two possibilities, greater equal 90 or less than 90. So let's assign this number 1, and we have two branches. So we put greater than 90 and less than 90 to the branches, not on the node, yeah, but to the branches, yeah, because these are two alternatives. Okay, then the second one is else if score greater than 80. Yeah, else if score greater than 80. Now you see that here, grade being assigned to A is if it's greater than 90, right? If it's greater than 90, then you see note number 2. Note number 2, we assign A to the grade. Yeah, because the input score is greater than 90. But if the input score is less than 90, we go to note 3. Now in note 3 here, we don't assign anything because in note 3, it is another decision. Elif score greater or equal to 80. So from here, yeah, number 3 here, we have two branches. One is greater equal 80. The other one is less than 80. Now, if we put the other way around, no, less than 80, the other one is greater than and equal to 80. Also fine, no problem. Yeah, also fine, no problem. So let's say the first branch, greater and equal to 80. So assign grade B. So let's follow this path. And for note 4, okay, we will return grade assigned with B. Yeah. Now, the other branch is less than 80, right? Which means that it goes to the next node. Elif score greater than or equal to 70. So here is 70, see? Less than 70, go to the next. If less than 70, yeah, go to the next one. If greater or equal to 70, then we go to note 6, which we assign with grade C. Yeah. So if it's not assigned grade C, then it goes to the next elif, right? So the next elif, the score is greater or equal to 60. So this is for one branch. Then the other branch is less than 60 lah, the opposite, the contra of it. So if it is greater or equal to 60, assign grade D. Okay, so note number 8, we put D. And then else, it moves to the last one, else. Yeah, it moves to the last one, else. Note number 9, assign with grade F. And then finally, don't forget, this is important. Yeah, don't forget, you must, all of this eventually return grade, right? So all of this must point to the last note, note number 10. Yeah, don't leave it hanging. Don't leave it hanging. Otherwise, your answer may go wrong. Okay. And now the numbering here is based on the order how you process the input. Okay. Now, if you prepare one today and then you prepare another CFG the next day, maybe the answer look different, but the logical flow must be correct. The logical flow must be correct. Now, what if the other day, next day, you forget how you draw it today, but when you draw it, the numbering is a little bit different. Is it wrong? Maybe, maybe not. I will go through the same flow, number 1, number 2, number 3, to see whether the flow is correct or not. Okay, so this is the answer, the control flow graph. But so what? This is not flow chart, it's a control flow graph. But so what? Why do we need a control flow graph? Because we want to interpret for testing. Now, first, we need to determine all the we need to determine the number of possible paths for the full coverage, minimum number of paths. So you can use McCabe complexity formula. Yeah, either here I use the variable M, but you can also use CC. Yeah, that's not so important. First, you need to know the formula. The formula is E minus M plus 2P. So E here refers to edges. Edges means arrows. N refers to nodes, which refers to the nodes, the circles. So you count how many nodes. 1, 2, 3. Apparently, number 10 is the last node, so you know there are 10 nodes. And then the edges, you have to count the arrows. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 arrows, or edge 13. Now, P here is the number of program. Here, we have only one program. Right? If we only one entry point, one program, one entry point, right? So P is apparently 1. So we take the formula E minus N plus 2P. 13 minus 10 plus 2, you get 5. So there should be minimum 5 test cases. Minimum 5 test cases. But the 5 test cases should not be repeating. It should not be repeating. It should cover all the condition. It should cover all the condition. So let us explore. Now, if you look at the graph here, yeah, you can actually trace the arrow. So you can trace the arrow by putting the number. For example, 1, 2, 10. Yeah, 1, 2, 10. So I miss out 10 here, but actually just let me write it here. 10. And then 1, 3, 4, 10. Next is 1, 3, 5, 6, 10. Next is 1, 3, 5, 7, 8, 10. Okay, correct. And lastly, 1, 3, 5, 7, 9, 10. Okay, so these are the paths to achieve 100% coverage. So to come up with the test cases, let's say we pick up number 1 path. Okay, number 1 path is taking what node? Node number 1, node number 2, and node number 10. So the first node is checking if it's greater than 90 or not. Okay, so we want to test this, right? The input will be, we want to test node number 2. So we will, how do we make sure that if we go 1 to 10, what is the input for the score? What is the score? Anybody? What is the score? Assign.
Depends on what we assign to the function.
Yes, but we want to put some value to make sure the code will actually execute along this path 1 to 10. So what is the input?
Oh, any number, any integer number between 1 to 10. And any
greater than 90 lah, right or not? It must be greater than 90, isn't it? If less than 90, it won't work, isn't it?
Yeah.
Let's say 100. To score. So what is the expected output?
A.
Yeah. Expected output is A. So in order to test path 1 to 0, I must make sure I assign input 100 so that the expected output will be A. So you see here, if we go here, you assign A. After that, it will jump out. So isn't it that we have just traversed path 1 to 10? 1 to 10, correct or not? 1 to 10. Now, let's say I want I want to test this route. 1, 3, 5, 7, 9. 1, 3, 5, 7, 9. So what is the input I should use so that I can test the code? I can do black box testing that the code is actually running 1, 3, 5, 7, 9, 10. I mean, black box, white box, that doesn't matter. I mean, in this case, okay, let's call it white box because we're using CFG, right? So how do we make sure that the code will be executed this way? 1, 3, 5, 7, 9, 10.
If you want to do the boundary, we can put 59. If you want to do the partition, you just pick any number between 0 and 59.
Yes, correct. So you can, for this, to make sure that you can test 1, 2, 3, 5, 9, 10, right? So you will use the value, the input value, 59 or any number. If you want to use partition, you're right. Yeah, let's say I use 59. Let me rub this off. Razor. So to make sure I actually cover 1, 3, 5, 7, 9, 10, okay, I now use input 59. And then the expected output is what? 1,
F.
2, 3, F, right? The expected output is F. So you see, just by looking at this, 1, 3, 5, 7, 9, yeah, we can already figure out that the expected output is F if the score is less than 60. Correct or not? This is how you determine that the input is 59. You see, because when you look at the expected outcome is F, right? Look up for the expected outcome, which is F, because I want to go by this path 1, 3, 5, 7, 9. Yeah, I want to make sure this path is tested. Just now we have tested path 1 to 10. Now I want to test path 1, 3, 5, 7, 9, 10, right? So I go to 1, 2, 1, 3, 5, 7, 9, 10, and then I say the expected output is F. So what will give me F is when score is less than 60. So I can put 59 if I want to use boundary. Now I can use smaller numbers. If you want to use the partition like maybe 15, 10, any number within. Yeah. So I know that the input is 59 and the expected output is F. This is one test case already. So you see, when I ask the tester to input 59 to the score, it will first test with 90. Nope. Test with 80. Nope. Test with 70. Nope. Test with 16. Nope. Display F. Return grade. You see? So it's going through this path, right? 1, 3, 5, 7, 9. Because it tests with 90, tests with 80, 70, 60. So now we have covered this path. Test case number 1, I use 99. Test case number 2, I use 59. Now, if I just ask you to figure out how do I test path 1, 3, 5, 6, 10. Okay, let me use another color of my pointer. I use green. Okay, let's try 1, 3, 5, 6, 10. What is the input and what is the expected output? Because we want to prepare the test case, right? So we already have 2 test cases. Now this is the third test case. So how do you figure out what is the input?
We can see that is less than 80, and it must be more than the 70, the one after it. So between 70 to 79.
6, 10, right? So the expected output is C.
See,
Correct or not? The expected output is C. And then just now you mentioned that you see in order for you to get expected output C, the S must be greater than 70, right? Yeah, the S must be greater than 70, but less than 80, isn't it?
yeah.
So you can choose 70 or you can choose 79 As long as within the range of 70 to 79, you can use 70, 71, 72, 73, 74, 75, 76, 77, 78, 79. So just pick any number. Let's say I just want to use number 70 lah, because I want to test the boundary, right? So that's it. If you use input 70, score 7, because I refer to input, but what is the input here? The input here is score, isn't it? The input here is score. So when I want to test 1, 3, 5, 6, I make sure it goes to 1, 3, 5, 6, then to 10. So I must use input 70. When I put 70, automatically it will jump to here. No. No. Yes. Assign. Get out from the function. I see. Now I have tested if score greater than 90, if score greater than 80, if score greater than 70, if score, yeah. But I haven't tested score greater than 60, right? And others. So because I haven't done for path 1, 3, 5, 7, 8, 10, I haven't done for path 1, 3, 4, 10. Now, do you see now why we prepare control flow graph? Because with the control flow graph, we can determine the McCabe complexity, the number of test cases needed. And then also by visually inspecting the control flow graph, we can determine the path. Okay, when we determine the path, okay, then we can determine the input and the expected output, right or not? So I hope everybody at this point of time can clearly see why we build it and how we use it. Don't just memorize why we build it and how we build it, but how to use it. Okay, the second one example is simpler. Again, it's a Python code, def check number. So this is one function only inside nested if else. Yeah, greater than 0 positive, less than 0 is negative, else the result is 0. So again, you will start with number 1 and you must return the result. Okay, yeah, start and end. You know, at first you don't put the number first because you don't know what's the last number, right? But of course, the first one you can put number 1. Then you check, okay, number greater than 0, left. Number less than 0, right. If greater than 0, return positive. If less than 0, I do the next test. You see, all the condition, right? You will label the arrow. All the condition, you label the arrow. But when you assign the result, you label the node, not the arrow. Yeah. When you assign the output, the expected output, you will put it at the node, not the arrow. The one that you put at the arrow is the if else. Yeah. See, if else. Yeah. So again, once you have a control flow graph, what you need to do is you determine the number of minimal test cases by using McCabe complexity, the same formula, but you need to count the nodes and count the arrows, edges or arrows. Yeah, edges is represented by arrow, and then because one program only, yeah, so just plug in the numbers and you get 3. So you know there will be three test cases minimal. And then there'll be 3 paths. So visually you can inspect 1, 2, 6, 1, 3, 4, 6, 1, 3, 5, 6. And then you can prepare the input and then determine expected output. So path 1, 2, 6, 1, 2, 6. What is the expected output? The expected output is positive, right? And in order to get positive, the input must be num must be greater than 0, right? So I put 5, 7, 8, whatever. So I will be able to get input. Let's say I put 5, then the result will be expected outcome is positive, right? So this is testing 1, 2, 6. You want to test 1, 3, 4, 6, 1, 3, 4, 6. So the expected outcome is result negative, right? Result negative. So I look at the condition before it is the num must be less than 0. Yeah, the num must be less than 0. Okay. Now this is one way of drawing it. But what if I want to put result negative straight away here? Cannot lah, because there another possibility is because result could be 0, isn't it? Yeah, result could be 0. So the num should be 0, yeah, but cannot equal cannot equal to 0. So the input less than 0, maybe you put -5. And then to test path 1356, 1356, the expected result is 0, right? So here you see, on the right hand side, I didn't put anything. Num is equal or less than 0. Here is num is equal or greater than 0. So the only thing that is equivalent after you analyze the condition is equal. So equal to 0. So the input is 0, and then you get the expected result, ZERO. Control flow graph example 3. You see, it's pretty much analyzing, it's pretty much the same thing, but the only difficult thing is depending on the type of control, the type of decision trees. If the decision tree is complex, then the graph looks more complex. Now this one is slightly more complex because you have if else, and then inside if you have another if else, inside else block you have another set of if else. So this one is not the direct nested if else. So how does the graph look like? Yeah. So you see, the output here is print both x and y are positive. Print only x is positive. Print only y is positive. Print neither x or y is positive. So because these are very, very long, I don't want to write it here. Otherwise, my graph looks very, very messy, right? So I would suggest that you create a legend in your final exam, or your test. You create a legend. Print A, okay. So you put a legend lah, print A, print B, print C, print D, instead of writing the whole thing. Then when you draw the graph, it'll be easier for you. So you start top down. Draw the graph. The starting point, number 1, is this one. If x is greater than 0. So number 1, you have 2 arrows, right? Because you remember, condition, you put on the arrow. Yeah. Greater than 0, less equals 0. Then, if greater than 0, inside here, another if else, right? You see? So from node number 2, you have another if else. Y greater than 0 or y equal or less than 0. All right. So if greater than 0, print both x and y are positive because it's a legend already. Else print B. Okay. And then for this part, you see, because this block, if y is greater than 0, falls under else, which is the pair of if x greater than 0, right? So it is the pair, right? So left arrow, right arrow. So you should put the note on the next arrow lah. Yeah. So from here, you include all this block. If y greater than 0, you put it under block number node number 5. So 6, 7. Yeah. If y greater than 0, 6. If else 7, and then print C, print D. And don't forget, because you see, in the end, whether we have the statement return or no return, we know that at the end of any function, if we return back to the main caller, right, there'll be a return, even though it's not shown here. So you must have the arrow point back to number 8, which is return. And then again, you determine the McCabe complexity by counting the nodes and edges. And here the calculation shows that there should be 4 cases or 4 unique paths. So the unique paths you can trace from the CFG 1238, 1248, 1568, 1578. So these are the 3 additional examples of control flow graph. We now move on to data flow graph. Yeah, data flow graph is not looking at if else. Data flow graph is looking at the variables, the parameters. That's how data flow graph is different. So let me show you. You see, this is one Python code, but the question is not asking for CFG, it's asking for DFG. Now the question can ask for both, draw the CFG, draw the DFG. But in this example, it's just asking for the DFG. Why DFG? Because we want to analyze the algorithm, how the algorithm changes the value of the variables. It's just like when you do coding, right? You have the watch, step in. You apply watch to any of the variables, step in to see how the values change, isn't it? It's somewhat like that lah. Yeah. So here, this is how you do it. You see, this is one function. Inside this function, we have how many variables? A, B, C. Is it A, B, C, right? And then number 2. And then D. D is, and also E. So A, B, C, D, E. And number 2. Yeah. Okay. And then that is number 1 thing you need to find out. So you identify already the variables. Then the next thing is you identify the operation. Sometimes not operation, it can be function. For example, ceiling, C-E-I-L-L, ceiling, you know, to find the ceiling value. Or round up, floor, to find the floor value. Or maybe it's a function that negates, or any function, you know. Not just operator. You can use, you look out for the operator plus the functions. But in this case, because we are looking at the content of calculate total function, so we don't bother about calculate total because we're just studying the inside. Just studying the inside, not the calculate total itself, the inside. Yeah. So we have a plus, multiply, minus. So how do we put all the variables and the operations plus, multiply, minus together? Now start top down, always like that. Top down. So we know already here A plus B. A is input, right? A plus B. So you see, A, B, you put them in a square. And then the operation is plus. You put the note as operation. You see, this is how it's different from CFG. In CFG, you are putting the arrow as if else. And then the notes are to assign to execute some statement. But in DFG, it's different. Inside the note, you're putting the operation. The operation can be numeric, it can be a mathematic operation like plus, multiply, minus, or it can be some unique function like ceiling, floor, absolute number, ABS. Yeah, not just not necessarily the mathematical operators. It can be the function operators as well. Greater than, less than, equal. So you see here in the first line of code, A plus B. So take A plus B. A plus B gives you C. See, at the bottom here, you put the output. Yeah, A plus B, you put the output. So you know that it's producing C. And then the second line, we done first line. Then the second line is we are taking C multiply 2. You see? So you find the operator multiply, you put inside the node, and then there's number 2, right? So now number 2 multiply with, wait, there's no C here, what? But wait, don't duplicate. Don't make unnecessary duplicate, because we know C is A plus B, isn't it? So we just borrow the arrow, just extend the arrow. No need to put another C here. Just continue. Yeah, because A plus B is C, what? No, not. A plus B is C. So just put the arrow continue here, pointed towards the multiply. You see? And then it produce what? It produce D. Okay. And then after that, the third line of code is D minus B, right? So is B up there? Okay, D is up there. Just reuse. And then draw the minus note first, then reuse B. And then up there, is there D or not? Wait, there's no D, right? But wait, check at the bottom. Oh, there's bottom. But we don't draw the arrow from the bottom up, isn't it? But wait, don't worry. Just trace back. D is traced back to multiply, right? So this multiply is producing D, isn't it? So just draw the arrow from here. That would have settled it. So after multiply, it gives you the output E. So you start with E. And then here, return E. Return E no need, because here we are not concerned about the control flow. We are concerned about the data, how the data value change when modified by operators like mathematical operators or function operators. Yeah. Let's look at second example of DFG. Okay, this one looks more complex. You see, this is a mathematical equation. Instead of showing you a code just now the example is showing you a code. Yeah, but here we are showing you a mathematical equation, not a Python code or any programming language code. So how do you do this? This is where you need to recall your mathematics. Anything inside the bracket, do first, right? So again, identify the variables. Variable A, variable B, C, D, E, F, G, H. Any number or not? Okay, no number. And then what is the other variable? Don't forget, result is also a variable, isn't it? Result is also a variable, but this is output variable lah. Correct or not? So how do we do it is we identify which of these need to be done first. Because like just now, when we look at code, we start from top down, isn't it? We do C first, D, then only E. In mathematics, we look at the bracket first. So A plus B must do first. We take A plus B. And then after that, C minus D, C. Okay. And then what else? E divide F, G multiply H. Okay, done already. Done already. Then the next, after we have this and this and this and this, the next thing we do is we do further. We do further, right? We take the result of this, multiply with the result of this. So we trace back lah. Okay, multiply. So we take AB, multiply with CD to settle this one. And then, same. This one also same. This one multiply, right? Take the result of this, multiply with this. Yeah, the result here is obtained here already, you see? So that's why the arrow is pointing to this. And then finally, we do the plus. Which is this, right? So we take the result of this plus with this. So the result of is coming from here and here, right? That's why the arrow is pointing towards the plus here and produce finally the result. Now, what is this T1, T2? Okay, these are just to label lah, no? Which do number 1, which number 2, number 3. It will help you to double check. Task 1, task 2, task 3. So task 1, A1. I do task 1, A1, task 1, A2. And then after that, task 1, B1, task 1, B2. And then the result of task, the result is merge becomes task 2A, task 2B. Okay. And then finally merge together task 3. Because here task 3 no AB because only one node for that level, right? So this one, you put A1, A2, A3, doesn't matter. You can just put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Also doesn't matter. Just put T1, T2, just to label which one happened first. Like just now, you see? T1, this one should be T2, a typo. Because it plus first, then we multiply. So typo, T2, and then T3. You see? Number 1, number 2, number 3. So clear? Any question? This is like a third time already we are looking at this with different examples. Because the best learning comes from doing examples actually. And just now I have submitted the following assignment in ULearn. And I hope you'll be able to analyze this problem and come up with a solution for CFG and DFG. This one looks like similar to CFG example 1, right? But wait. Yeah, this one is more complicated. Why? Because it's inside a class. It is inside a class, right? And then inside the class, you have 2 methods or 2 functions. Sorry, 3 functions. In constructor, set marks, and calculate grade, right? So, what should we do about this? How do we come up with a control flow graph? How do we come up with a data flow graph? So I throw this challenge to you. And then after that, you determine the minimum number of test cases needed. Okay, you determine the minimum number of test cases needed. And then propose the test cases input and expected output. All right, I think that's about it for today's additional lecture. And this lecture is actually going to cover for next week. All right. And I will leave this assignment for you to do next week and the following week. And if you have any questions, you can throw the questions in our Facebook group, STQA. With that, I would like to end the lecture. Thank you very much for having me. And now I open the session to Q&A.